Everyone will be starting in 2 minutes. Yeah, so let's get started. I'm Udipta, and along with Aditya, we'll be taking the sessions for astrophotography learner space. And today's topic is imaging systems from the first module that I shared. So let's get started. Imagine it's the year 1839. Telescopes already exist. People can see the moon, stars, but nobody can capture what they see. The night sky is beautiful, yet impossible to preserve. Then, in 1839, everything changed. For the first time, a picture of moon was taken. Humanity had pictured a piece of universe for the very first time. A few years later, in 1850, astronomers photographed a star called Vega. So it might sound ordinary, but at that point of time, it was not. In fact, it was revolutionary. It became the first star apart from the sun whose light was successfully photographed. For the first time, people could study a star without looking through an eyepiece. The story didn't stop there. Scientists soon realized that starlight carries secrets. By studying Vega's spectrum, astronomers could identify the elements present in stars. As you can see, in 1872, Henry Draper was successful in capturing Vega's spectrum. Fast forward through photographic plates, CCD cameras, and today's CMOS sensors, as you can see here. Now, anyone with a camera and a telescope can capture galaxies millions of light years away from their very own backyard. So, the terms here, CCD and CMOS, are pretty interesting. So, let's go through them. Let's understand what they actually mean. So, CCD here stands for Charged Coupled Device. So, both of these, first of all, are sensors. So CCD is a type of image sensor which is used in cameras, especially it was used in older astronomical cameras. So let us understand how it worked. So light from a star hits the CCD sensor, then each pixel converts incoming photons into electrical charge. The charges are transferred across the chip to a readout circuit. The camera then converts the charge into a digital image. Think of it like as a green as a grid of tiny buckets. More light, then more electrons collected. Then less light means less light collected. So CCDs were revolutionary because before CCDs, astronomers mainly used photographic film, which captured only a small fraction of the incoming light. So now let us move towards the next. Yeah. Next, we have types of astronomical imaging system, which is the wide field system and the deep sky imaging system. Just wait a moment. So yeah. So wide field imaging, for wide field imaging, we use wide lens or a telescope with short focal length to photograph a large section of the sky. For example, look at this picture. Think of it like taking a landscape picture with your phone, that is wide field, and zooming into a single mountain, and that is called narrow field. In astronomy, wide field imaging shows large constellations, galaxies like the Milky Way, meteor showers, and star trails. Now, let us understand deep sky imaging. Deep sky imaging focuses basically on very faint nebula or very faint objects such as galaxies, nebula structure. These emit very little time by the this emit very little light by the time they reach Earth. So the key difference between wide field imaging and deep sky imaging is wide field imaging captures large area of the sky, And deep sky imaging captures faint light from distant objects. So the next type of is planetary imaging. Now, planetary imaging is quite different from both wide field imaging and deep sky imaging. This is because planets are much closer to us in comparison to other celestial objects. So, unlike galaxies and nebula, these objects are bright, relatively close, and they are small in apparent size. So, here the slide says we require short exposure times. Now, short exposure time prevents overexposure and it freezes atmospheric turbulence. What I mean by that is for capturing images of celestial objects like galaxies, we require large exposure times, which we record in minutes. But since planets are much closer, then the exposure time that we require is generally in milliseconds. So if we take pictures, if we the exposure times are increased to minutes, then the picture would be completely washed out. So we require much short exposure times in comparison to wide field and deep sky imaging. Now, the next here I mentioned is video capture. So the says here short clips are taken, sharpest frames extracted and composited. Now, what happens here is several pictures are taken. The sharpest pictures are picked up, and then they are aligned and they are stacked. We have then the stacked image is carefully processed in software like Cyril or GIMP. The next one is spectroscopy. This does not involve exactly capturing of image, but it involves recording and analyzing the spectrum of light. So why do we need spectroscopy? So first, what we can understand is the composition. What elements are present in the celestial object that we are observing? Hydrogen, helium, or oxygen. Then the temperature. Hotter stars, as we know, have different spectral patterns than cooler stars. For example, blue stars are hotter and red stars are cooler. Next, a very interesting thing is mentioned in this slide, which is velocity measurement via the Doppler effect. So if an object moves towards us, Doppler effect says that wavelengths get compressed. So spectrum shifts towards blue. This is called the blue shift. And if it moves away, wavelengths stretch. So spectrum shifts towards red. And this is called red shift. Yeah, let's move on to the next thing. Yeah. So these are basically the components of the entire system that we are studying and using to capture the image. So this is in itself is not very complicated. This lists down the components. So you all can read it by yourself. So here CCD and CMOS both are mentioned here. So yeah, so CMOS is high resolution, low power, and affordable because the pixels in CMOS have electronics inbuilt in themselves, so they don't have to go through the same process as CCD. So yeah, let's move on. So this is arguably the most important slide of today's session, which is the imaging system. So let us understand this in great detail. So let's explore this first. This is the, I'm sorry, this is the primary imaging telescope. This is the main telescope that gathers light from galaxies, nebula, or star clusters. And think of it as a lens of the whole system. So it has its aperture, it has its focal length. So the aperture determines how much light it can collect, and the larger the aperture, the more the light and potentially more detail. The focal length determines the field view and magnification. Shorter focal length, wider view, and longer focal length, narrower and more zoomed in view. The same thing as a narrow field and wide field, as we discussed earlier. So the telescope, it focuses light directly onto this one shot color camera. Short form of it is OSC. So the name one shot, it's is there because a single exposure already contains color information. So one other type of camera is also used, which is the monochrome camera, which has a much more complex workflow than this, which we won't discuss today. So the one shot camera, what it does is it takes many exposures, as we discussed earlier, which are later stacked and processed. So the next very important part of the imaging system is guide telescope and guide camera. So they are not directly involved in image capturing, but they do something pretty cool. So let's understand it. So this is a small telescope which is mounted on top. Its job is not to take the final photo. Instead, it watches a single bright star. So is it necessary that the bright star would be part of the celestial system that we are observing? No. So the it could be any bright star which perhaps is nearby to the system that we are observing. So why do we require a guide telescope and what does this even mean? So these mounts, what they do is when I input the data that I want to observe a certain galaxy, then this slews the focus of the system towards that target. But but even good mounts can have tiny tracking errors. So if, for example, we are doing deep sky imaging or wide field imaging, then we require long exposure times. So in this long duration, errors can turn stars into streaks because the position of stars would change relative to us. So the guide scope acts like a spotting scope that constantly checks where the mount is drifting. So next we have the guide camera. It's attached to the guide telescope. It continuously measures the position of the star. If the star even moves a few pixels relative to us, the software sends correction commands to the mount. This process is called auto guiding, and this is very important in imaging system. Auto guiding is what allows us to take long exposure times while still keeping the stars round. So now the next things which we have is the go-to equatorial mount. This is arguably the most important of the entire imaging system. So what a go-to means basically selecting a target. So what it comprises, it performs two jobs, go-to pointing and tracking. So if you select an object, let's suppose I'm observing the Andromeda galaxy, the mount automatically slows to the target, just as I mentioned before. So what it does is it also tracks. The Earth rotates at 15 degrees an hour. The mount rotates the telescope in the opposite direction so that the object stays centered. So this is a very important task because this prevents misalignment, and if we get misaligned pictures, then they will not be stacked properly and we won't get the data that we want to observe. So now why do we need a specialized mount like this? So simple tripod cannot do this, and we manually cannot handle this system. Without tracking, stars trail after short exposure. So next what we have is the electronic polar scope. So the for the equatorial mount to track accurately, its rotation axis must point towards the celestial pole. So the electronic polar scope helps you to perform the alignment precisely. Think of it as a built-in alignment camera that helps the mount to aim correctly. Next we have the Wi-Fi camera controller. It's pretty self-explanatory. So with this, even when we are not besides the system, from far away, we can start and stop exposures, change camera settings, or monitor progress. So uh, yeah. So let us first understand the entire process again. Basically, how, like, what's the entire workflow that happens here? So first, light from galaxy enters the primary telescope. The telescope focuses the light to the one shot color camera sensor. Then, meanwhile, when all this happens, the guide telescope and the guide camera, they are continuously focusing on the guide star. So even if a tiny error happens, the corrections are sent to the equatorial mount. The guide software detects tiny tracking errors. The mount keeps the target precisely centered during long exposures. Many exposures are captured and then later stacked in software. So we are done with this. This was pretty important. So next we move on to multi-wavelength imaging. So yeah, this topic is about how astronomers capture different kinds of light from space. The key idea here is the universe doesn't only shine in visible light that we can perceive, it emits radio waves, infrared waves, UV rays, X rays, gamma rays. Each wavelength reveals something different. So these are some techniques to help us analyze and understand each and every single waves. So first we study radio waves, and the first way is radio astronomy using interferometry. So instead, what we do here is instead of building one giant telescope, astronomers connect many smaller dishes together. So together they behave like one enormous telescope. So the reason why they do this is because it provides higher resolution and higher detail. So the next way of observing technique of observing radio waves is the single dish observation. It's opposite to this. Instead of several dishes, we have one large radio antenna collecting radio waves. So it's used to study pulsars and solar flares. So the next one is pulsar timing. Just I mentioned pulsars here. So what is a pulsar? A pulsar is a rapidly spinning neutron star. It emits radio pulses so regularly and in a definite frequency that it acts like a cosmic clock. So it might sound fancy, but let me explain what this actually means. So by measuring tiny changes in pulse arrivals, so these pulsars are pretty frequency efficient. So if the frequency changes at a certain point of time, so scientists can study extreme matter and detect gravitational effects. This is because pulsars normally send pulses after exactly 1 second. But suddenly, if a pulse arrives a tiny bit late, then something must have interrupted the path. So what must have happened? So this leads to more study. A planet might be orbiting the pulsar, or a gravitational wave might have stretched the space, or the pulsar itself might have changed. So astronomers use these perfectly regular pulses like a stopwatch to study the universe. So next we study infrared rays, and the first one is space-based telescopes. So why do we require space-based telescopes? Why do we have telescopes located outside of Earth? So the Earth's atmosphere absorbs almost entirety of the infrared light. So telescopes are placed in space. One famous example that all of you must have heard is the James Webb Space Telescope. So they can see cool stars, dust clouds, and star forming regions. So next one is ground-based infrared. So in the Earth's surface, where we do this is in high mountains, which have thinner and drier air. So the reason is less water vapor means less infrared absorption. This allows infrared observations from Earth itself. So next we study ultraviolet rays. So UV rays come from very hot objects like young stars, hot gas, or active galaxies. Because Earth's atmosphere blocks most of UV light, astronomers use space telescope like the Hubble Space Telescope. Then UV spectroscopy is basically understanding the spectrum of UV light. So using the after analyzing UV spectra, astronomers can determine the chemical composition, the temperature, and the motion of stars and galaxies. Next, we have X-ray telescopes and gamma ray telescopes. Now, both of these have very high energy and frequency. They come from X-rays come from the most energetic places, black holes, neutron stars, supernova remnants. Normal mirrors don't work for X-rays because either it passes through them or it gets absorbed. So instead, X-rays must skim across mirrors at very shallow angles, like grazing incidences. So next we have gamma ray telescope. They are the highest energy form of light produced by supernova explosions, gamma ray bursts. And scientists use special detectors because gamma ray passes through normal lenses and mirrors. So there are two pictures which I've used here. One is of Saturn and the second is of Cassiopeia A. So this image is from the infrared region. The infrared region detects the temperature difference, atmospheric structure, and features available in ordinary visible light images. So next we have Cassiopeia A. So here only one wavelength is not used. It is a mixture of several wavelengths. No single wavelength here tells the entire story. That's why multi-wavelength imaging is so powerful. It combines many views of the universe into one single picture like this. So yeah, we are mostly done with the theory part and we will be moving on to image processing now. So if everyone has installed Cyril and GIMP, we can continue. Okay, does anyone have any doubts? Okay, if no one has till now, we will move on to the image processing section. So everyone make sure you have Cyril and GIMP installed once again. And in the drive link that I've shared, make sure you open the .fit file. Um, so when you click that, it will direct you to Cyril itself. So yeah, let's start with the image processing part, the fun part. So I will directly move on to Cyril. So let us first get familiar with this. So this is what you will observe once you open Cyril. So this says m16stack.fit. That's how I named it. So first of all, you will observe this dark image right here instead of any color. So let us first get familiar with the interface of it. So this is the console right here, and these are and here right here you can see it's linear written over, and we have this drop down menu, and we have auto stretch here. So let's see what happens when I click this. So magically the nebula started to appear out of nowhere. I did nothing here. But this is not what we want, because auto stretch is just a preview of what the data should look like. So it's just a temporary display adjustment that makes dim pixels brighter so that you can easily see that on your screen. So just as we saw, when we first load any picture, it comes out, it almost every time it will come out dark like this. So what AutoStretch does is brightens the faint details, increases contrast, and makes nebula and galaxies visible, but it does not change the actual image data. So it might be overwhelming at first, but let's understand with this analogy. For example, you have a picture in your phone, and the brightness that the setting in the settings you have brightness very low. So when you increase the brightness, you can see the picture more clearly. But it does not mean that the brightness of the picture itself has increased. What you have changed is is brightness in your phone rather than the picture itself. So that's how works basically. It's not very complex. It's basically a preview of what the image should look like. So what do we need to do in order to get an image out of this very black picture in front of me? So what we do is something called stretching. Now, what is stretching? So when we load this picture, almost all pixel values end up clustered near the dark end of the brightness scale. This is because stacked images are linear images. So if one pixel receives 100 photons and other receives 200 photons, the second pixel is stored at exactly twice as bright. So the number is fixed, so it's linear. But after stretching, it becomes a non-linear image, which is optimized for our vision. So stretching redistributes the brightness values, so faint details become visible. So here's an analogy again. So imagine you are listening to a recording where someone is whispering. Information is present, but it's too quiet. Stretching is like just turning up the volume. You are not creating new information. You are making existing information easier to perceive for human eyes. Now, again, stretching is important because the nebula, without stretching, the nebula looks black, galaxies look invisible, and dust lanes just disappear. Most of the hours of exposure seems washed. So before stretching, there is one more thing that we need to do, which is called background extraction. So for this, I will use auto stretch, that is the preview mode. So now here you can observe one important uh, task of auto stretch. So when I click background extraction here, so what does background extraction mean? So make sure you have polynomial selected here. You have order 2 here. What background extraction does is, for example, if I place a tiny red square here, so what it does is it sends information to Cyril, and what I want is a uniform background without noise, without any turbulence. So essentially, what we expect in such an image is the background to be completely dark. But here we see green tint, we see whiteness, we see the image a bit whitewashed as well. So, for this, background extraction becomes extremely important because what it does is it takes out all the noise and it tells the this tells the software that this is not what we want. We want a uniform we want a uniform brightness across the entire background. So in order to do this, first use add dither image, add dither, because while recording this data, some streaks might have been observed. So after compute background, sometimes we see disgusting green lines here, and we don't want that. So make sure you have add dither selected. Then we can use generate option. So this generates all the red boxes that we need. But make sure that you don't have any selected right on top of the nebula because the nebula does not comprise the background. This is the brightness of the nebula is what we want to increase. To make sure right click is to add a square and left click is to remove a square. So make sure you manually remove those squares. So you might think that uh, we could have manually placed the squares itself. Yes, you can do that, but we, for appropriate background extraction, we need as many red boxes as possible. And this generate option works pretty well in that case. So removing some boxes is much easier than placing so many boxes. So yeah. It might take a while, but it's certainly faster than manually putting boxes here. Yeah, we're almost done with it, and we don't want any on the nebula. So when I click compute background here, we see the nebula instantly becoming much more brighter. We see an enhanced contrast here. So we click apply and we see a much brighter nebula thanks to background extraction. The next thing which we move finally towards is stretching. So there are four types of stretching, but first we will learn the last one, which is generalized hyperbolic stretch transformation. This is the easiest type that you can do. So yeah, let's get started. So what GHS does essentially, let's understand what these mean. So what GHS does is it lets you brighten the mostly the faint and the medium bright parts. So this is the histogram. So this is the x-axis. X-axis represents the the brightness of pixels, and this represents how many pixels are present of that brightness. So right now, we have a very zoomed out version of this, and we need it to be zoomed in. So make sure you select 90 here, and then you click here. Yeah. So make sure you use this slider to place this here at the very center. So now we will learn something called the symmetry point. So this is the symmetry point. It says there is no selection. So I will choose this point. Look closely. It says clicking on the histogram sets SP. So I have selected the stop portion right here.
भाई मेरे को
The
समझ नहीं आ रहा। इंटरनेट चला गया मेरा।
As anyone has a doubt? Yeah, so let's continue with some disturbance. So yeah, so one thing which I missed here is again we don't do stretching in auto stretch mode, but we do it in linear mode. So yeah. So now I was explaining what the symmetry point is. So basically, when I select this point right here, what I mean is stretch the picture around this pixel value. So this is the pixel value which is most concentrated right here. Most of the pixels have this brightness. So what is it what this it's telling the software is focus the stretch around this brightness level. So
Mm.
since the peak contains most of your faint nebula and background data, place the symmetry point. Placing the symmetry point there makes the GHS work on the faint stuff. So here it is. So now what I want to do is pull this slider to its maximum value, that is 15, because what it's telling the software is stretch strongly around the symmetry point. So yeah. So next, what we want to do is zoom out right now, and we will do something interesting. You can just click one right here. It will do its job. What we'll select here is logarithmic scale. So why logarithmic scale? Because logarithmic scale makes the histogram much easier to see. A logarithmic view is like using a magnifying glass on a crowded region. So even small differences become visible. So now we are all set and we can start stretching. So I want you to pull the slider till we start observing nebula. You can see the stars have started appearing, and we can see the nebula is appearing. So make sure you keep stretching until and unless it gets too washed out. So we don't want this a little bit less. Yeah. So this much is sufficient. And then we finally click apply. Now close this window and we observe this image. So you might have seen the contrast is getting a bit, it's still a bit whitewashed right here. And we want this to look pretty. So what we do is we stop at Cyril and we go on to the next software, which is GIMP. So we save this in format called TIF rather than FIT, just the opposite. So I save this like this and click save and use 16-bit unsigned integer instead of 32 bits because GIMP can work its very best in 16 bits instead of 32 bits. So click save and we will move on to GIMP. So here using the file option, you select open and then you the TIFF that you saved right here, you just double click on it. And everything is fine here, don't worry, and just click keep. We have this image right here in GIMP. So, so we will keep it very simple for today's session. We will just use three things to bring out the nebula that we desire. The first is levels and then curves. Let's start with levels. So again,
Udipta,
here is, yeah,
I think someone has a doubt.
okay. Ujjwal, can you speak up or you just press the raise button by mistake?
Hello, am I audible?
There you are.
Yes. So, sorry for saying this so late in the lecture, but I am not able to open the. Like, I click on the fit file, but it takes me to this the other site you sent. the other link, which was, I don't know, this GIMP, not the Cyril. It's taking me to the other link.
The fit file.
Yes.
So you can do a simple thing. Just go to Cyril,
Uh,
click
right.
open here, and just find the file here. You can
Right.
do that instead of
Okay.
just clicking it.
Right.
So let's move on.
Udipta, you're muted.
Refer it. Okay. So let's understand the histogram here. So okay. So here you observe a white mountain shaped graph. This again shows the x-axis and y-axis stand the same again. It shows how many pixels at what brightness value. So when you pull this black slider left, you see a washed out version, but when you pull this right, you see a darker background version. What it does is it makes the darker pixels more darker. It works on basically the dark pixels, the ones with faint details. And when I pull this, it brightens the darker pixel. It brightens the brighter pixels or the pixels of medium brightness. So we don't want it to be washed out again. Yeah, yeah, this is mostly fine. So you click OK here, and we go to a more advanced version of basically creating contrast here, which is curves. So here we will learn something called S curves, which is a very, very important tool. It's like a much more powerful tool than GHS or histogram transformation. The x-axis again stands for current brightness of pixels, and the y-axis stands for the new brightness after adjustment. As you can see now, the curve is linear. So if the input pixel value is 20, then the output pixel value is still 20 because I haven't adjusted anything here. So if I pull, so this portion, it stands. So look at this. So its x coordinate is also has a small value, and its y coordinate also has a small value. So what it means is that it has it has fewer pixels in this region. So it determines the darkness of the pixels that we have. So this region is the represents pixels with lower darkness. So if I pull this down, what it means is I am dimming the brightness of those pixels which were already dark. The Where do we find dark pixels? It's mostly in the background. So is it desirable that the background becomes darker? Yes, that's what we want, because that would also result in the nebula getting brighter. So now what does this stand for? This stands for the highest pixels having the highest brightness values. If I lift this up, what will happen is the what will happen is the brighter pixels getting more brighter. So the brighter pixels are mostly in the nebula region that we want to work on. So this works, and this is almost shaped like an S. If I put this down, and here we go. We have perfect S right here. That's what was desired, and we are done with this. We have a mostly black background with a proper brightness. At this point, what we can do is crop the picture a bit, press enter, and we have a more zoomed in version. The last thing which we can do is a pretty simple thing, which is the arranging colors and fiddling with the colors of the pixels. So if I move this slider towards red, so this number means it's getting towards the red side. And if it goes negative, it goes more towards cyan and it becomes less red. So if I increase it, just as I increase it, you see the nebula getting more red. So you don't want it to be too red just like this, because this would result in us losing data. So we will push it to generous value. And we can also, so magenta, if I this is negative, we can get a magenta color instead of green. And green noise is something which we always try to avoid. Pull this up a bit more. And here we go. Okay, it's a bit too red. So you can reduce it. Yeah, we are mostly done with our very first processed image right here. So if anyone has a doubt, you can ask in image processing.
First, I have to do this all by myself. I just started the process.
Don't worry about that. I will provide a detailed guide to how you can exactly get what I have done right now. So you can follow the steps, and for further assignments and all, you can use those steps as a guideline. So
Okay.
I'll be sharing that document.
Okay.
If anyone has any doubts, you can ask. This is the chance. Otherwise, you have to follow the document. If you want to ask, you can ask right now. It could be pretty overwhelming, but
So, is it
yeah,
audible?
yeah.
Actually, during the starting part, actually, I missed what to do. So, can you just repeat the starting part of it? Just a little bit. What to do actually for color that is.
Right, all right, we can. Yeah, so let's go to Cyril again. So here I will, using open, I will select that. So this is the one. So yeah, so here you can observe this is completely black right here. So right now, this is because it is in linear mode. So there is one option which we can take to observe the nebula, which is auto stretch. But auto stretch is just a temporary solution to it. This is because auto stretch is just a preview regarding what the nebula could actually look like. So the reason why we get a linear image being so black is because if one pixel receives 100 photons and other receives 200 photons, then the brightness of the second picture would be 2x more than the brightness of the first picture. So, so in order to uh, reveal the nebula details, what we try to do is stretching. So what stretching does is briefly it redistributes the brightness values so faint nebula becomes visible. So before stretching, we do one more thing, which is the background extraction. So we go to background extraction, we make sure you have polynomial and degree order 2 selected, and you click generate, and you deselect those squares which fit directly on top of the nebula. So right now we're just doing rough, so I won't deselect much of them. Like you already did it with this ones. So right click, you add these boxes, and left click, you remove them. Yeah, now it's mostly rough. So I'm using compute background, and you see the nebula getting much more better than before. I click apply, and then I move on to stretching, which is the GHS, which is generalized hyperbolic transformation. So the histogram right here is too stretched, too zoomed in, so we need to zoom out. So we select 90 here, and we can observe a zoomed in version. Make sure this is selected right in the middle using this slider. Yeah. So, okay. So here we use something called the stretch symmetry point. So what symmetry point is if I select it here, selected here, what it says is clicking on the histogram sets SP. So I have selected this point as the SP. So what it does is this pixel, this brightness value has the maximum pixels right here, as you can see. You can see the peak right here. This says that focus the stretch around this brightness level and focus the stretch around this brightness level since the point contains most of your faint nebula and background data. So placing the symmetry point here makes GHS work on the faint stuff. If I select this, then I stretch local intensity to maximum because it says stretch strongly around the symmetry point. So next what I do is I zoom out, just click one here, it's built in, and use logarithmic scale. We use logarithmic scale because it's like a magnified version of the linear one. It's, it it helps us to spot even small differences. Small differences become visible here. So right now we can start our stretching process. So what we want is it to be linear because again we are working on linear data rather than auto stretch. So we stretch the stretch factor. We pull the slider until and unless we observe the figure. So yeah, that was it.
Okay, thank you.
You understood?
Yeah, I understand.
Okay, so the assignment will be out shortly, and the one with the best processed image will get featured in our newsletter. So I encourage you all to complete the assignment. And yeah, so if you have any doubts, we can also conduct doubt sessions. So if nobody has doubts, anymore, then we can stop this session.